In this next little portion of the video, we're going to look at an example or two. So, okay, pressure and temperature are the easiest variables that we can measure. But for a pure substance, that's going to be a liquid-vapor mixture. And so they're not independent. So if I want to determine the quality of a saturated mixture, I usually use something called a Throttling Calorimeter. Now essentially what this is a valve that's going to drop the pressure to a point where it's a superheated vapor. And so if I have a sample, we're going to take one that's at 1 megapascal, and I'm going to send it through this Throttling Calorimeter, and it's going to come out at 50 kilopascals and 100 degrees C. And let's see how we can use this to figure out what the quality is of the wet steam. So the given information, it's a throttling valve. I've got water flowing through it. The inlet pressure is 1 megapascal, the exit is 50 kilopascals and 100 degrees C. I want to find the quality at the inlet. So this is a steady state system, so there's the energy balance. It's only got one stream in and out, so mass flow in and mass flow out will be the same. So I can eliminate those summation signs, and I can divide through everything by the mass flow rate. Now that is going to change these to Q dot over mass flow rate, which is just the specific amount of heat transfer and the specific work. Okay, so that's first. I have a throttling valve. So a throttling valve is going to be small device, not much space for there to be a heat transfer. There's no moving parts, so work is going to be 0. And the inlet and exit are going to be at essentially the same elevation and the same inlet size, so the same velocity inlet and outlet. So what I'm left with for my energy balance is simply Hn equals H out. So what I need to do is I have two pieces of information about state 2, the exit. I need to find that data, use it in this first law, the simplified form, and then see how that helps me. So if you go to the data books, and in the course management system I have a set of steam tables, or you can use the one from your textbook. And I found that the enthalpy at the exit was 2,682.5 kilojoules per kilogram. That means that at the inlet it was also 2,682.5 kilojoules per kilogram. Now this helps me because that plus the pressure is two pieces of information. Two pieces of information, I can go to the data and I can find the final state. So if I do that, it's going to be saturated. We knew that, right? It's at 1 megapascal. I look up the liquid and the vaporization enthalpies. Use that to calculate X. And this was 95% vapor. We'll do a second example, a pump. Now in this case I'm going to take water again. I'm going to take it from a sump tank, which is a tank underground so that water can drain, like maybe rainwater. It drains into the sump tank and then you need to pump it out to get rid of it every so often. And so in this case it's going to go from the sump tank to a vessel 10 meters above it. The water is going to flow at 3 kilograms per second. It's going to enter at 5 megapascals and 100 degrees C. It's going to exit at 30 megapascals, so a much higher pressure, and 100 degrees C. So the temperature change is very nominal in this case. We'll assume the pump is adiabatic, and what we want to know is what's the power input. Again, translate that given information. So M is 3 kilograms per second. The elevation change was 10 meters. At the inlet to the pump, it's 0. It's at the low elevation. And at the top, it's at the high elevation, so I said that was 10 meters above it. P1 and T1 are given. P2 and T2, the exit, are given. It's well insulated or adiabatic, so Q is 0. I'm looking for W. This is my energy balance. Okay, so this is going to be 0. I only have one stream in and one stream out, so I can get rid of that, and I can divide through by the mass flow rate if I wish, but they gave me the mass flow rate, so that isn't necessary. I'm never going to assume that the enthalpy in and out are anything other than different, okay? And I have no reason to believe that there's a change in kinetic energy, so these will be 0. But the potential energy change, I do have 10 meters. So my simplified form is this. Now, it's not nearly as simple as the last one, but I can look up data. I have the inlet and the exit states well defined, so I know what the Z is. I can use the P and T to find the enthalpy. The mass flow rate in each case is 3 kilograms per second. G is the gravitational acceleration of 9.8 meters per second squared. I know everything, or I can find everything other than the power. This should be easy. So go find that data. Again, using the data set that I provided in the course management system. These are the values I found of HI and HE. And then I'm going to start plugging those in. But now I want you to think for a moment about the units. H is in kilojoules per kilogram. I'm going to add to that GZ. G is in meters per second squared. My Z is in meters. So I'm going to take kilojoules per kilogram and add meters squared per second squared. You can't add things unless they have the same units. So I need a unit conversion. Very handy, 1,000 meters squared per second squared is a kilojoule per kilogram. So if I do that, I can just plug the numbers in, make sure I fixed my units, which I did in the calculations, but I noticed that when I typed it here, does not say 1,000, where it should. But when I did the calculations, this did in fact include the 1,000 there. So here is my answer. Negative 57 kilowatts. By remembering to do the unit conversion, again, not this one, but this one right here, what you will see is that this second term, the potential energy change, is very small compared to the enthalpy change. It's not negligible, but almost. So I end up with negative 57 kilowatts is the energy change. So we'll stop there. We'll come back and we'll do a couple of other examples in the next lesson.